This is a work done by Dzonou, which is a student on the Siconos project, and he's now at Saint-Étienne after being in Lisbon for 1.5 years. And myself and Paoli. The problem is maybe well known for people who have been hearing me for the last 20 years, almost. So the setting is we are studying a finite dimensional system, which is must be the motion must take place in a set L, which is given by just one unilateral constraint. And I denote by u plus the right derivatives, u minus the left derivatives, and we know that by kinematical constraints that u plus must be in the in a tangent cone, which is this set V. And since we expect discontinuities of velocity, we introduce the measure, the Stills measure, to be considered as the acceleration. We have the balance equation, the mass matrix M multiplying this acceleration, this measure, is equal to some given force times the Lebesgue measure plus reaction. The reaction is also a measure, I denote by dr. So we are dealing with normal reaction, so minus dr must belong to the outward normal cone to the set V, to the cone, which is also the tangent cone. In inelastic contact, one privileges the right velocity, u plus, and we have this formulation by Jean-Jacques Moreau, which is minus the reaction, belongs to the outward normal cone to the tangent cone at u plus. Consider. So, because in the simplifying case that I've considered first, when I studied this in 85, the identity matrix, at a collision or impact, the reaction has an atom, so we can say that minus dr is u minus minus u plus. And indeed, this equation, this inclusion already tells us that u plus must belong to V. And in order to have the outward, the normal cone not to be reduced to 0, it must belong to the boundary. And then the reaction is normal, and you get this projection of u minus, u plus is just a projection of u minus into the miscible set V for velocity. So, in the case of a partial elastic contact, this formulation can be also done, but instead of considering u equal u plus, we have just an averaging between the right and left velocities, u plus plus e u minus divided by 1 plus the restitution coefficient e, which in this case belongs to 0, 1. With 0 we obtained the previous case. So you have the similar differential inclusion, and for instance, for the perfectly elastic case, we have just the average between the two, and the average must belong to the tangent hyperplane, and we get the usual perfectly elastic law. So we can formulate by replacing minus dr by its formula, by given the balance equation. We have this differential inclusion, measure differential inclusion, because we have measures in it, and it's the force times multiplying the bag measure minus the mass matrix, the measure of the acceleration belongs to the outward normal cone to V at u of t, where u of t is this average velocity. So this, as I told, is a formulation that was introduced by Moreau. I had studied in '85 the case, the inelastic case, E equals 0, with the identity matrix, and the force not depending on the velocity. It's only f of time t and position q. And then Mabrouk in '98 published, solved the problem for the general case, but still with identity matrix, mass matrix, and with a force not depending on the velocity. Related works, but in a somewhat different spirit, were done by Schatzman, Paoli, and Wallach. And then for friction, there's another which is so. I consider so the mass matrix is a positive definite matrix, which is C1 and globally Lipschitz, in order to not having to deal with a lot of technical problems for estimates. We have already enough in this setting. Then we have the inverse matrix, the square root matrix, and I assume that there is this correspondence between the usual with the norm and the norms determined by M and the inverse matrix. The function given the unilateral constraint is supposed to be in C1 1/2. For Mabrouk, this was C1 beta, with beta larger than 1/2. And in the elastic case, C1 is just enough. And then the external force is smooth, also globally bounded and globally Lipschitz, so that we can at least treat the local existence case, and then the global existence requires further energy estimates and can be delta. So we have this formulation: find the velocity u, in fact the averaged velocity, which has bounded variation, and by integration we obtain the motion q, the displacement, and satisfying this differential inclusion, whose sense has to be precise. So in fact this means that we have a measure for which there are densities from the Lebesgue measure with respect to mu, and also from the acceleration with du with respect to mu. And for these densities, the differential inclusion is satisfied d mu almost everywhere. So this is the precise meaning of this measure of differential inclusion. And one good thing is that we can perform the numerical scheme by just discretizing the interval, the time interval, then starting from initial positions q0, u0, updating the position by using the previous velocity, and then using this formula to find the next velocity at time tn I plus 1. Where we do a projection with respect to the relative to this norm, this coordinate norm. Here is you have to use the inverse matrix, and this is the admissible velocity set at the new point. And we can use this in an implicit in the velocity, at least in the computation of the term force, or explicit. You can do the same thing. Then we define un of t by uni, and then by integration approximate function qn. Then it can be shown that these approximate solutions are bounded, and even the velocities, so that we can extract a subsequence converging uniformly for the displacement. But the most important part, and it's difficult at this estimate level, is to show that the total variations of the approximate velocities are uniformly bounded, and then we can extract something which converges pointwise to a bounded variation function v. Then we average to obtain the what we want to show that it is a solution, this function u. And in fact, this is so. The inelastic case has been completely treated by Dzonou, and you'll show some numerics. Also, for the general case, it's done more or less in the same lines, and that's just my last transparent before passing to numerical experiments, which will be shown by Dzonou. My last slide. For the inelastic case, of course, free motion is usual ODEs, can be shown easily. Continuity points where the velocity is continuous in contact, are studied by obtaining this kind of variational inequality, where you can use as a test some points which belongs to the tangent cone when we stay in the neighborhood of the limit trajectory, and from that use derivation of measures to obtain the result. And impacts are studied by detailed analysis of the numerical, the discretized scheme. We have to show that there must be a discrete impact when we are sufficiently for sufficiently large n, for sufficient small discretization step, and then study what happens about the variation after this first discrete impact to show that it satisfies the inelastic shock contact law. The right velocity is the projection of the left velocity. And for the general case, it's more or less the same scheme. We study free motion, then continuity points, we obtain the same variational inequality, and we have to study the impact law. And when one tries to control the variation after first impact, there appears the need to change the assumption, to have a more stringent assumption on the boundary of the set. So before passing to Raul, we want to weaken some assumptions and obtain global solutions, and of course one would like to treat and mainly to obtain results for multi-contact. So I think I can stop this general part and then pass to
Okay, the physical model is double on the loop, and we fix an impact only on the first wire. You have a mass here, and the motion of the second wire is free. So what we are expecting for is to verify all the theoretical results that we obtain in the mathematical study. So now we can write the equation of the motion, and so x1 and Packet 1 is the coordinate of the first wire, and then X2 and Packet 2 is the coordinate of the second one. So when we wrote the Lagrangian, we have this one, and we take the unknown as theta 1 and theta 2 as the angle of the first wire, and theta 1 is the angle of the first one with the vertical, and theta 2 is the angle of the second wire with the. So theta 1 and theta 2 are those angles that we are trying to verify that the first one will stay in the. We verify the impact law. So, and as you see on the pictures, so we fix an impact law on the first wire is that the angle will not pass p divided by 2 and minus p divided by 2. So when the angle is p divided by 2, we apply the impact law related to the restitution coefficient, which is between 0 and 1. And using Moreau formulation, we can write this problem as differential inclusion. And we have our inertia operator, and we can verify that this inertia operator satisfies those conditions that we mentioned in the theoretical study as is symmetric and definitive positive matrix, and we can find Lipschitzian or C1 condition. And on the first term too, we can verify all those results. So okay, I will just remind the numerical algorithm. So the numerical algorithm is this one, and we just remind that we call that the main problem is that we have all the time have to be close to the local metric, and here we use an implicit algorithm to the velocity, because it's just a simple numerical scheme, and at every time step we have to make a kind of fixed point to choose the right velocity and then continue. So now I will show the result that we obtained in some case. So we just take the mass of the first wire equal to 1 and the length equal to 1. So we compute with a time step equal to 8 seconds, and we take the gravity equal 9.8. So the initial angle is 60 degrees with so this one is an elastic contact case, and then you can see on the pictures, this one is the motion of the second wire. So we can verify that after the first impact, because the restitution coefficient equal to 0, the first wire will stay on the obstacle and will not have any bounce. So in the second case, we can verify, we try to compute the kinetic energy, and then we saw this discontinuity, so we have only one, because we have only one impact, and it's an inelastic case, so after we have a kind of regularity which corresponds to a periodic movement. So this one is linked to the second wire, which is continuous, the motion is free. And then we try to verify our computation by looking at on the total energy. So we only have one jump, and after we have a conservation. This one is on the case A equal to 0. So after we move to, we have tried to compute the restitution coefficient. equal to 0.7. So we can see that the first the first wire will bounce, and at one point it will stay on the movement will stop, and the second one will continue with regular position. So the time step is 0.1. So we have the two positions, and in red you can see the second one. So we try at the same time to verify, to look at the kinetic energy. It would be nice to superpose the curve, because we can look at that the impact time. We have a kind of coincidence, but because of the scale, it's not very nice to see on these pictures. So we move to the total energy to be convinced. So those curves, our result was because after we have a motion, we have a conservation of the total energy that corresponds, because the first wire is now it stopped on the obstacle, and the second one is continue, and those kind of discontinue correspond to all those bounds that we have. And we move to A equal to 1, which corresponds to an elastic case. So at this moment, we just focus ourselves on the first wire to see how the movement will move. So we have those kind of bouncing, and we try to take the time equal to 20, and there is no stop, and otherwise we have the bounce. It corresponds to an elastic movement. And to convince ourselves, we have tried to compute the total energy. I will stop this. And so we can see that in the case of A equal to 1, we have the conservation of the energy, and our theoretical result has been verified in those computations using the sweeping process method. So that's all.
Can you put up figure 1 again, please? I was expecting some feature of some discontinuity in the motion of the second wire.
Okay.
But I didn't see it. I'm not sure how to explain that.
Yeah.
So the red curve,
yeah.
I thought at a point 5 or so, which is where the impact occurs for body 1, or wire 1, I thought I would see a discontinuity also in body 2. Unless perhaps it was horizontal at the time of. So I expect to see a discontinuity in the red curve, and I don't see it. So that's my question. Shouldn't there be a discontinuity there? The coupling between the bodies would cause?
I'm not really sure, because at the beginning the two on this position, the initial data are taken on point at the angle at 60 degrees, and then after we have this movement. So maybe the first one is going faster than the second one because of the effect of the mass, and not.
So well then I guess my second question: the subsequent motion I thought should be sinusoidal.
Yes.
And it's not sinusoidal if I.
Yes, because of those points, and I have discussed with some.
It's
not a linear pendulum.
It's not a.
This is not the velocity.
Okay.
I have a question. Can you bring the slide number 4? I want to look at the algorithm. Wherever the algorithm is.
Okay.
Yeah, the same. Yeah. Take a look at this. So this is an
60, whereas one of them starts with
Yes.
one starts
So
with
how
6.
density?
was not
So
20
how do
minutes,
you,
for sure.
how do you solve it?
But I don't know what it was.
What kind of a problem is this? This is a finite dimensional, so things are implicit. So what sort of how do you actually solve? How is this being solved?
We use a fixed point algorithm.
Oh.
It's because there is okay when you have when there is no contact, the algorithm is very simple because you have this space equal to the whole space.
Right.
So you have just to compute a sample.
But you don't know whether there's contact or not, right? So that's part of the.
Yes, yes.
So you use a fixed point algorithm for.
Yes, we have a task first.
Yeah.
If the point is the constraint is violent or not. So if when the constraint is violent, we are okay. We first make the fixed point without any projection, and we have to verify if our velocity is an admissive velocity. If it's the case, so we continue to the next
Do you know the fixed point algorithm actually converge? That you actually prove that it solve this problem?
Yes, yes. So we have in the elastic case, yes. When we take okay, there is a first computation because we have to take a time step that verify this contraction condition.
But I'm talking about the discrete time problem.
Yes.
This one, you use a fixed point algorithm to compute to solve this.
Yes. So the hypothesis that you have on F is that F is Lipschitz in respect to the third variable. So when you apply the Lipschitz condition, we can. So here we have a projection.
In some cases, you can compute this.
I see.
In this Siconos example, I think you can almost compute the projections. So
Yes.
But then it's implicit. Everything is implicit here. Maybe. So. Anyway, so I can ask you later. Get more details. Are there other questions? So as not to delay the lunch.
Well, first, Professor Stewart mentioned that I agree with him, and there are several examples about that. That when you have slender bodies and using a restitution coefficient might lead to violation of energy. Did you have some special initial conditions in your computation where you could find such a violation?
I should answer to your question. If you work with generalized coordinates, if you apply the restitution coefficient model, you cannot have a gain of energy. It is impossible. There is energy
In
consistency.
this kind of system?
Yes.
Okay.
So we have to check it numerically, of course.
Okay.
But in the model, it is included.
maybe to simplify the model for this.
No, but this is a simple problem. It's special. Okay, I take the answer.
One last question.
And just a question. Usually, when we want to ensure energy conservation, we use midpoint rules or trapezoidal rules. So here, you have just completely explicit, explicit rules for your displacement, and you are able to conserve energy. So I don't understand how you can do that numerically. So perhaps there is a trick.
Trick is in the proof, so it's quite complicated, but
Okay.
check it.
No,
So-
but they prove only that they conserve energy in the limit. So the question is whether energy is conserved at impact. You're talking about conserving the energy over the whole duration of the simulation.
Yeah, yeah.
Yeah, no, so
Because
that's a matter of the method, and you can
Okay,
prove
you
it
have-
only in the limit as a time step goes to zero.
okay, you have choose a very, very small time step. Okay, in
Yes.
this,
When we
Plus,
prove
keep in
the
mind he has very
convergence-
simple constraints. That's
When we prove the convergence, we have to check that there is a kind of conservation of energy for the discrete system. So there is, when we prove a priori estimate, some kind of energy estimate which is behind the mathematical aspects.
But then you have the second
Okay.
terms from F which you cannot cancel.
Sorry.
Then you have the second terms from F which you cannot
Yes,
cancel.
but in your model, when you don't have
Right.
any impact,
That's right,
you can
when it's
gain
linear.
energy through 12. That's the physics.
So on these pictures, you can verify that, okay, if you are in a very close neighborhood of the impact point, you have a kind of conservation of the energy because the curve is like that. So if you move a little, so when the time set will be more small, maybe we can have some curve and we can verify the law. This one is the kinetic energy in the case of equal to 1. So we was trying to look at if the impact law was verified that we have a kind
So
of.
this question had to do with whether the energy is conserved for finite time step, not as the time step goes to 0,
Yes.
which is the symplectic aspect. That was not the case here. So.
I think we should have lunch. So let's thank all of you.
Yeah, we can leave your